Hi, Dr. P here, and in this lecture video we'll take a look at gases, namely pressure and gas laws. In future lecture videos for this chapter, we'll look at the ideal gas law, as well as doing stoichiometry with the ideal gas law, and a few other aspects of gases, such as the kinetic molecular theory of gases, which is an explanation for the gas laws, as well as looking at some real gases. All right, so let's get started. As you know, a gas is a state of matter that has a indefinite shape and volume. It assumes the shape and volume of its container. So gases are unique in that respect. So you can change the volume, you can squish gases, you can expand gases, etc. One characteristic of a gas is pressure. So gases will exert pressure on their surroundings. And this is typically the walls of the container. Although if you happen to be inside a container with some gas, like let's say you're in an airplane, and you will feel a change in pressure as the airplane ascends and descends, as the cabin pressure, the pressure of the gas, air in the cabin, changes. Meanwhile, the pressure in your ears has not changed quite as quickly, and so you feel that as, well, pressure. There are some other things we use to characterize gases, namely volume and temperature and number of moles of gas, but we'll get to those when we talk about the gas laws. Now we can measure pressure with a barometer or a manometer. And manometers are used for general measuring, whereas barometers are specifically measuring atmospheric, sorry about that spelling, atmospheric pressure. So how does a typical barometer work? Well, let's take a look here. So we'll have some kind of container, usually a long tube, and we'll fill it up with some kind of liquid, often mercury. You could do it with water, but you'd have to make the tube of water 30 feet, 30 feet long, tall. And so we have a tube filled with liquid. For example, mercury inverted in a dish of the same liquid. So I've got my liquid here, and my liquid inside the tube will actually drop down a bit. We'll have something like so, and then we can measure the height of this column of mercury. And just want to mention that, so we've got our Hg is in here, and just want to mention that this column of mercury is held up by atmospheric pressure I'll just abbreviate that as atmos. Atmospheric pressure pushes down on the liquid in the dish, and it pushes down with enough pressure to support a column of mercury. And typically, H is going to equal 760 millimeters of mercury for standard atmospheric pressure. All right. And atmospheric pressure, of course, is going to vary with altitude. Obviously, at higher altitude, there's lower pressure. You go up to Tahoe, and it's lower atmospheric pressure there. And it also varies with weather. Weather meteorologists will talk about, in their weather reports, will talk about areas of high and low pressure. Now, a few words about units of pressure. So we'll typically use millimeters of mercury, or torr, T-O-R-R, lowercase, named after an Italian scientist named Torricelli, who took his tubes full of mercury up and down various mountains in Italy to examine pressure. And this is like back in the 1700s, I think. 1800s, I'm not sure exactly when. 1700s, I think. Anyway, one thing to know is that 760 torr equals 760 millimeters of mercury. So 1 torr is the same size as a millimeter of mercury, which equals 1 atmosphere. ATM is atmosphere pressure, and these are exact. Now, pressure, of course, is a force applied over an area. So I could say P equals F over A, a force applied over an area. And then in the SI system, that's going to be newtons per meter squared. And so we call 1 Newton per meter squared a Pascal, big P, little a. Named after Blaise Pascal, the scientist and philosopher. And 1 atmosphere, let me just scoot this up a little, there we go. 1 atmosphere equals exactly 101,325 pascals. It's about 1 times 10 to the 5th pascals. There are some other units of measurement. We have the bar, which is 100,000 pascals exactly. And we have PSI, pounds per square inch. And atmospheric pressure, 1 atmosphere, is approximately 14.7 pounds per square inch. So it's not, that's not an exact conversion factor. I'm not going to write it out here. So let me just go ahead and box these so you can highlight them. Don't worry, I will give you these conversion factors on other group activities and exams. All right, so that's pressure. Now there are some other things that can be used to describe gases. Things, it's such an imprecise word. There are some other characteristics of gases that can be used to describe gases. So one of them is volume, and this leads to the first of our gas laws. So these are really the behavior of gases in general. Okay, they are a generalization, and in many cases, gases do follow these laws pretty well. So the first one is called Boyle's law. And what Boyle found was that pressure times volume equals some constant. If we looked at some data, it would look something like this. If we had pressure versus volume, we get this kind of curved relationship here, but it is an inverse relationship, whereas our pressure increases, our volume decreases, and as the volume increases, the pressure decreases. If instead we plot volume versus 1 over pressure, we actually get a linear plot. So this is volume on the y-axis, 1 over pressure on the x-axis. So we would say that volume equals some constant times, let me rewrite that, sorry, volume equals some constant times 1 over P. And so if you just multiply both sides by P, the pressure, you get PV equals the constant. Now gases that follow Boyle's law are called ideal gases. Ideal gases. And we'll take a look at ideal gases and what kind of assumptions we have to make to consider a gas to be ideal. We'll look at that a little bit later. But there are a couple of more gas laws that I want to get into. And I also should mention that, real gases may deviate from this ideal behavior, and it depends on the circumstances. So there's another named gas law, which is Charles's law. And Charles studied balloon flights and the relationship between volume and temperature. And so at a constant pressure, volume is proportional to temperature. So that is, if we plot a volume versus temperature plot here, we'll get a straight line like that. So another way of saying this is volume equals some constant times temperature. And of course B here is some constant. T is the temperature in Kelvin. Okay, you have to measure the temperature in Kelvin, all right, because we can't have a negative volume, so we need an absolute temperature scale. So speaking of that, that implies that at absolute zero, gases have zero volume, which of course is probably physically impossible, right? Because the atoms themselves have to take up some volume. Well, it turns out that's one of the assumptions we make when we talk about ideal gases, and we'll look at that a little later. Another gas law that we should know about is Avogadro's law. And what Avogadro discovered was that equal volumes of gases, and they could be different gases, if they're at the same temperature and pressure, they contain the same number of particles. So particles, atoms, or molecules of gases. Or we could write volume equals A times N, where A is some other constant, and N is the number of moles of gas particles. Okay, so we could combine these into some form of a combined gas law. And, I should note that Avogadro's law applies even if we've got even if we have different gases that we're comparing. So a liter of, a liter of oxygen at 1 atmosphere and 273 Kelvin is going to have the same number of particles as a liter of hydrogen at the same temperature and pressure. So let's combine everything together. Excuse me. And I think that's a good place to end. So we know we have, so I'm going to say combining gas laws. We know that we have volume equals some constant over pressure. Volume also equals some other constant times temperature. And volume equals some third constant times number of moles. And we can combine these into volume equals some combined constant. It's the universal gas constant. It's basically combining mathematically K, B, and A. And that's times temperature times number of moles divided by pressure. Or PV equals nRT, which is, as some of you may know, the ideal gas law. And R has a value of 0.08206 liter atmospheres per mole Kelvin. All right, so this is our ideal gas law. Very important. You should, give it to you on assignments, but you should memorize that. And again, this is ideal behavior. So a real gas may be different. We could also combine. Now notice that we could say PV over PV over NT equals R. So I could then say, P1 times V1 over N1 times T1. So for gas 1, we have that, and then that equals R, but that also equals P2 V2 over N2 T2. So we get a combined gas law. Which would be P1 V1 over N1 T1. And oftentimes N doesn't enter into it because we keep the moles of gas the same. and that equals P2V2 over N2T2. So we can describe any any ideal gas using pressure, volume, number of moles, and temperature. Pressure, volume, temperature, and then number of moles. And there we go. So in the next lecture video, we'll take a look at the ideal gas law in a little more detail, and some other, doing calculations with the ideal gas law, doing some stoichiometry. But until then, stay safe out there. Bye now.